All right, so we're going to go ahead and get started on section 4.1, and it is broken up into two separate sections, or two different pieces, mainly because we usually can't get through the whole section 4.1 in one class period. So I am going to break it up into section 4.1a and 4.1b. However, for the online section of this class, you're going to need to watch both videos in order to do the 4.1 assignment in my math lab. Okay, so both videos will be embedded in that assignment, so make sure you watch both of the videos before you attempt that homework. Okay. All right, so I just kind of want to refresh on the unit circle, like where we've come from, okay? So far we've dealt with trig functions in terms of x, y, and r, right? And then we talked about trig functions with right triangles. And then we went into finding the reference angles, right? And then we introduced the unit circle, which is where we restrict R to be 1. And when we restrict R to be 1, it's easier to have an angle that's corresponding to a length. It also gives us something that we can graph an XY point, right? Because our angle is now a real number value. And we also can define our trig functions in terms of just x and y, because now that r is 1, remember our sine value is our y value, and our cosine value gives us our x value. So I want to just really quickly kind of just refresh on what we've talked about in regards to this unit circle. So remember, this is where we start at 0, right? And then if we make a full rotation all the way back around, that puts us at 2 pi, right? Halfway around, or half a rotation, is pi, right? A quarter rotation at 90 degrees puts us at pi over 2. And then 3/4 of the way around puts us at 3 pi over 2, right? And then we talked about each of these little angles, right? These are our happy little reference angles that we can easily find trig functions for. So like 30 degrees, we know that that's pi over 6, right? And all of these can be converted by just multiplying by our conversion ratio, right? 45 degrees becomes pi over 4, 60 degrees becomes pi over 3, and then we can figure out all these other values off of just these three, right? Because they're going to have the same XY point. The only difference is going to be the signs based on what quadrant they're in. Okay, so remember, if I wanted to find the point corresponding to where a 30-degree angle intersects the unit circle, all I have to do is look at that reference triangle, right? If this is a 30-degree angle, I can find my sine value by doing opposite over hypotenuse, right? Same thing with my x. I could figure out my cosine value by doing the adjacent over the hypotenuse length. But a lot of these reference angles for 30 degrees, 45 degrees, and 60 degrees, they come out kind of wonky, right? Sometimes we get a nice one, like 1/2, but a lot of times we get a square root of nasty over something, or something over a square root, right? So the angles that I want to focus on are the quadrantal angles. Okay, the quadrantal angles, because if I were to write the XY point for them, or here, let me write a different, pick a different color. If I wanted to write an XY point for our quadrantal angles, and we're limiting our R, right, to be 1, then this would be the point 1, 0, right? Up here at 90 degrees, or at pi over 2, this would be the point 0, 1. Our point over here at 80 degrees, or at pi, we would end up with -1, 0. And then our 270 degree intersection point would be 0, -1. And these are a lot nicer x and y values to deal with than the x and y values that are like, you know, square root of 3 over something, right? Or 2 over the square root of 2 and things like that. Those come out kind of wonky, right? So I'd much rather use these nice quadrantal angles because they have nice x and y values. Does that make sense? Okay, so notice we can go all the way around the circle, and we're going to call that one cycle, okay, or one wave when we go all the way around the circle one time. But I could keep going around the circle multiple times, right? And if I keep going around multiple times, like if I wanted to go all the way to 6 pi or 8 pi or 12 pi, right, I'm going to be hitting these same numerical values every time I go around and hit a quadrantal angle, right? So this is kind of the most important for moving forward into Unit 4 is we're going to focus on the cosine and sine graphs first, and then we'll do the other trig functions because they're very similar. Okay, so I want to focus just on sine and cosine because those are really easy to do with our xy points here. Okay, so again, I'm just going to focus on these quadrantal angles. So what I did and what might help you through this section is you're not going to need all of this, but I would go ahead and just kind of jot down on a piece of paper our unit circle with just our quadrantal angles. Okay, so you can put it on a little note card. You could just rip off a little piece of paper and kind of have it next to you when we're going through these problems so that we have these points to reference. And we want to make sure that it's in the radian measure. Okay, so we're going to go ahead and instead of putting 0 or 360, we're going to call this 2 pi, right? So we're going to go from pi over 2, which gives us the 0.01, to pi, which gives us -1, 0, down to 3 pi over 2, which gives us 0, -1, and then back up to 2 pi, which is 1, 0. Okay, so I'm going to pull this out from time to time as we're working through these problems. So again, if you want to just kind of jot this down on a little piece of paper you can have by your notes, that might be really helpful. Okay, all right, so first of all, on page 2, we're going to introduce the sine graph. Okay, so you can see here it says graph y equals sine x over a period of 2 pi. Okay, so I'm just going to point out some things. So whatever it's equal to y here, right, this is our dependent variable. Because y depends on what we, oh, that should probably be an A, dependent. Okay, y depends on what we plug in for x, right? Whatever we plug in for x, we're going to take the sine value of that, and that gives us our y. So that means that our x is our independent variable. Okay, so just noting a few things. So x, we're going to enter our x values in radians. Okay, so that's our radian measures going around. So our pi over 2, our pi, our 3 pi over 2, our 2 pi, right? And then y, we're basically saying the output that we get is going to be defined by the sine value, okay, or the sine of whatever radian measure we're looking at. Okay, so this is going to be, because we're dealing with sine, we're looking at the sine function, this is going to be the y coordinate on the unit circle. Okay, all right. So what I want to do, because I want to end up with nice, pretty sine values, not things with square roots, is I want to make sure that the x's that I pick in radian measures are those nice quadrantal angles. Okay, so I'm going to say use quadrantal radian measures. Okay, so if I pull my circle out here, my nice radian measures is when I start at 0, and then I go to pi over 2, and then to pi, and then to 3 pi over 2, and then I complete the circle at 2 pi. Okay, so I'm just going to put in those radian measures. I start at 0, then I go up to 90 degrees, right, which is pi over 2, and then I go over to 180 degrees, which is pi, and then down to 270, which is 3 pi over 2. And then I complete my circle back over at 2 pi. Okay, so I've specifically chosen nice radian measures that have pretty sine values, right? So now all I have to do is at each of these x values, I just have to look and see what its corresponding y value is. So when I'm at 0 here, notice the y value at 0 is 0. At pi over 2, my y value is 1. At pi, my y value is 0. At 3 pi over 2, my y value is -1. And then when I complete my circle here at 2 pi, my y value is back at 0. Okay, so just pulling those straight off the unit circle. Okay, so now it's important, the way that I'm going to label this. Okay, I know you could just put tick marks for each of these, but I'm going to label it in a specific way, and this is how we're going to model it going forward, because they won't always come out to nice things. We might have to kind of finagle this. So what I'm going to do is, this is basically saying it's going to go from 0 to 2 pi. So here's where 0 is, and I'm going to say, okay, 2 pi, let's just say 2 pi is here. Okay, so then halfway between 0 and 2 pi would be halfway to 2 pi, right, which is just pi. And then halfway between 0 and pi would be pi over 2. So we're counting by pi's over 2. So this would be 1 pi over 2. This would be 2 pi's over 2. So our next point would be 3 pi over 2. Okay. Again, on this one, we already knew all the points. It was really easy to just write them out. But I want you to get used to this, the strategy of putting your biggest point and then finding the halfway mark and then the halfway mark, so that we know how to label these. Because we might have to count additional points, and we want to make sure that we know what that unit is. So here, right, we're counting by pi's over 2. And then we go over here, this is a pi over 2. And then this is another pi over 2, right, as we keep going. All right, so let's go ahead and draw in our curve. So at 0, I'm at 0, so that's my point here. At pi over 2, I'm up at 1. So I'm just going to label and say this is 1. Okay. At pi, I'm down at 0 again. At 3 pi over 2, I'm down at -1. I'm just going to go ahead and label this -1. And at 2 pi, I'm back up at 0. Okay. So then when I draw my curve, I want to do my best to make these look like half circles, because really that's what this is representing, is all those sine values that we get as we go around the unit circle. Okay. All right. So this is what we call our sine wave, right? Or the graph of our sine function. Okay. Now, our sine wave, for right now, we're just going to do 1. This is one full complete cycle to go around the circle one time. But like we said, we could keep going around the circle multiple times, over and over and over and over and over and over, right? So we could keep going. This sine curve could continue on and on and on in both directions, right? We could continue it on this way, or we could continue it on this way, right? So the whole thing is called a sine wave, but just to complete one full cycle of the sine wave is what we call our period length. So here, to do one complete sine wave, our period length is from 0 to 2 pi, which means that our period is a distance of 2 pi. Okay? And then our amplitude, this is how far away from the vertical center is our maximum and minimum value. Okay? So if we look at our sine curve here, notice our maximum value is up here at 1, and our minimum value is at -1. So that means our vertical center is at 0, right? So if I'm looking for amplitude, amplitude is the distance from our vertical center up to our max, or our vertical center down to our minimum, right? So we can see here from our vertical center to either of those values, it's a distance of 1, okay? And I'm just going to write over here, this is how far away from the vertical center is the max and min value, okay? So if you're looking back at your notes and you're like, I don't know how we got that. Now we know, okay? All right, so what we should know is that a sine wave does continue on and on and on in both directions, right? So our domain, right? Our domain on a sine function should be negative infinity to infinity if we think about it going on and on and on and on and on, okay? That's why it is called a periodic function. It keeps going on and on and on, but it repeats that one cycle over and over and over and over and over and over again, however far we extend it in one or both directions, okay? All right. There will be some homework assignments. I know there's a worksheet that goes with this this section that may say, you know, graph it over one period. So here it says graph it over a period of 2 pi. So we just wanted that one rotation, right? That one cycle. But there may be one where it says graph it over a period of 4 pi, or graph it over a 2 period length. So if it wanted us to graph it over a 2 period length, we could do 2 rotations, right? Or I could have done a rotation in this direction to extend it a further rotation, okay? All right, so this is what our sine wave or our sine function curve looks like. So now we want to look at what our cosine function looks like, okay? So again, we're going to do it over 2 pi. We're still going to pick those nice radian measures, right? So that we can go around our unit circle and have nice, pretty outputs. But this time, because we are looking at cosine values, right? Cosine values we get from our x-coordinate, right? Remember when we did our sine curve, we got all of our outputs, all of our y values came from the y-coordinate on the unit circle because we were looking at the sine, right? So now that we're looking at the cosine, the difference would be that we're going to use the x-coordinates on the unit circle, okay? All right, so what I would like for y'all to do is go ahead and pause the video, and I want y'all to fill in the nice radian measures, right, from 0 to 2 pi, and then fill in the outputs, and then I would like for you to graph it and see if you can figure out the period and the amplitude, okay? If you get done and you're ready to check yourself, go ahead and unpause it, or if you get completely stuck, just go ahead and let it play, and we'll go through it together, okay? Okay, so let's go ahead and see how you did. So again, just like our sine curve, we're going to be using our quadrantal values, right, xy points. So since we're doing the cosine curve, this time we're going to be looking at the x values. So at 0, we should be at 1. At pi over 2, we should be at 0. At pi, we should be at -1. At 3 pi over 2, we should be at 0. And then at 2 pi, we should be back up at 1. Okay, so just copying those values over, I went ahead and put them in our chart here. Okay, so these are our nice quadrantal angles. Okay, our quadrantal measures in radians. And then I just wrote down the x value at each of those. Okay, so when we graph it, we can see at 0, we're up at 1. Pi over 2, we're down at 0. Pi, we're down at -1. 3 pi over 2, we're back at 0, and 2 pi, we're back up at 1. Okay. Again, when we graph it, remember these values are coming from a circle, so we want to do our best to get kind of that semicircle curve here. Maybe not my best work, but you can see here this is half the circle, right? and then here's the other halves of the circle. So this one makes a little bit different shape, right? But you can see here some things that hadn't changed is that our maximum is still at 1, our minimum is still at -1, and our vertical center here is still at 0, right? So if our vertical center is at 0, then our distance from that vertical center up to our maximum or down to our minimum is 1. So our amplitude is still 1. And notice we completed the whole cosine curve in a 2 pi period, right? So one trip around the circle is a distance of 2 pi. So that is our period length to complete one full cosine rotation, okay? All right, so now that we know what the cosine and sine functions look like, now we want to get into transformations. So if you will, go back in your mind to when you took college algebra. If you took college algebra with me, I hit you over the head with transformations again and again and again. So hopefully this will not be highly offensive. But remember, transformations is when we take our graph and we either stretch it or shrink it horizontally or vertically, right? We move the whole thing up or down, left or right, okay? That's what we're going to be looking at doing with the sine and cosine functions. So the first one we're going to look at is vertical and horizontal stretches and compressions, okay? Now, remember, when we look at vertical, vertical relates to the y, horizontal relates to the x, right? So anything that is happening horizontally or relating to the x is going to happen inside the function. So inside the sine or inside the cosine, right? Anything that happens vertically that affects the y is going to happen outside the function. So outside of the sine, outside of the cosine, okay? So, let's see. Yeah, I don't think I'm going to write that. Okay, so let's look at the amplitude. So the amplitude, remember, on both our sine and our cosine from our vertical center to the maximum or a vertical center to the minimum was 1, right? It went up to +1 or it went down to -1. So the amplitude can only be changed if we multiply our y's by a value, because that's either going to stretch out those y values or it's going to compress those y values. So to determine what our amplitude is, what we're going to do is we're just going to take the absolute value of whatever that A number is that's out front, okay, whatever that constant is, okay? All right, so the reason I put absolute value is because, remember, if this happened to be a negative A, if there was a negative out front, that actually is a reflection, okay? And we'll get into some of those here in a little bit, okay? Our period length, we know for both sine and cosine, to go one time around the circle is a period length of 2 pi, right? Now, if that gets changed, the only way that that could get changed is if we have stretched or shrunk horizontally, right? Instead of doing from 0 to 2 pi, maybe we stretched it out and it goes from 0 to 4 pi. Or maybe we condensed it to where it only goes from like 0 to pi over 2, right? So when we stretch and shrink horizontally, that affects our period, and that comes from this b value that's being multiplied inside the function, okay? So to figure out what our period is for any given sine or cosine function, we take our original period, which is 2 pi, and we divide it by the absolute value of b. Again, we're using the absolute value of b because if b happens to be negative, that actually relates to a reflection, okay? All right, so just for example, if we look at the example below, okay, example below, right, we have y equals, here, let me just write it, y equals 2 sine x. So if I wanted to figure out the period on this, I would do 2 pi divided by the absolute value of b. Now b, remember, is the number that's being multiplied by the x. So if I look in here, there's no number in front of that x, so it's an implied 1, right? Or in other words, this would just be 2 pi over 1, which is just 2 pi. So on this example below, our period has not been affected, right? Because we did not have a b value in front of that x. So our period should still be 2 pi. Okay. Our amplitude, however, for this example, remember our amplitude comes from the little a that is being multiplied in front of our function. So here we're going to do the absolute value of 2, because 2 is what's in front of our sine function, and the absolute value of 2 is just 2. Okay, so just as a side note, our amplitude is affected by the a value in front of the function. Okay, so in this case, 2. Okay, and then we're looking for our period. Remember, this one is affected by the b value in front of the x. So on this one, there's no issue here. No issue here. And we showed that with this example, right? All right, so let's go ahead and fill in our values. We always pick those nice radian values, right, that come from our unit circle. Because this is a sine function, we are going to be using the y values as we go around, okay? Now, this is something that you're going to want to memorize. You're not going to have this little circle available to you when you're taking tests. So we need to know we're going to go from 0 to pi over 2 to pi down to 3 pi over 2 and finish at 2 pi. Okay, our y values as we go around. Now, I'm just going to put a little extra column in here just to show what our sine values are. Okay, so when we do our sine value at 0, it should be 0. Our sine value at 90 degrees, remember, we're going to be up at 1. Our sine value when we get down to 180 or pi is going to be back at 0. Down at 3 pi over 2, we're at -1. And then when we complete our circle rotation, we're back up at 0. Right? So this is what we did on the previous pages, right? Just coming up with that nice sine curve, right? But now notice the only thing that's happened is we have this 2 that's being multiplied by our sine x. Because it's outside the function, it affects the y's. So basically, we're just multiplying all of our y values by 2. So 0 times 2, 1 times 2, 0 times 2, -1 times 2, and 0 times 2. Okay, so when I write all those, and you don't even have to write all those if you can do it in your head. I'm just putting it there so if you look back at your notes, like, where did we get that? You know what you did. So this becomes 0, 2, 0, -2, 0. Okay. So we're going to go ahead and graph it. So notice we're going from 0 to 2 pi. Half of 2 pi would be pi. Half of pi would be pi over 2. So that means we're going by pi's over 2. So 1 pi over 2, 2 pi over 2. Our other point is 3 pi over 2. And then we're going to put in our values. So notice our y values are all going to be 0, 2, or -2. Here's 1, here's 2, so -1, -2. So at 0, we're at 0. At pi over 2, we're up at 2. At pi, we're back down at 0. 3 pi over 2, we're down at -2. And 2 pi, we're back up at 0. And again, we're going to try and create our pretty curve to the best of our ability. Okay, so you can see we're still getting that nice sine curve. The only thing that changed on this one is our amplitude, right? Because you can see here from our vertical center up to our maximum or down to our minimum, our amplitude is now a distance of 2 units. Okay? All right, let's look at another one. Let's do another one. Hopefully we can get the hang of this. Okay. Oh, not that page. All right, so let's look at this one. This one says we want to graph y equals negative 1/2 sine x over one period. Okay, so it's not telling us what our period length is. It's just saying we want to graph it over one period. Okay, so remember, to find our period, we do 2 pi divided by the absolute value of b, where b is the number in front of x. So notice here there's no number in front of the x, so it's an implied 1. So 2 pi over the absolute value of 1 is just 2 pi over 1, which is just 2 pi. So we have no issue, no change here, right? Our period should be from 0 to 2 pi. Then we want to look at our amplitude. Remember, our amplitude we get by doing the absolute value of a, right? And a is this number that's in front of the sine function, right? So we're going to do the absolute value of negative 1/2. Absolute value of negative 1/2 is 1/2. So what that tells me is that from my vertical center up to my maximum, or my vertical center down to my minimum, should only be a distance of 1/2. Like our last problem, remember, it was 2. It was 2 units from the vertical center. So this one might be a little bit squished, okay? And then a reflection comes from a negative. So yes, here we can see we do have a negative, right? And the negative is outside the function. So if we are negating our y's, right, what that does, think about it. If you take your positive y's and make them negative, or you take negative y's and make them positive, that's reflecting your picture around the x-axis. So this is a reflection about the x-axis. Okay, negating our y's flips about the x-axis. Sorry, I kind of squished it in there. Okay. All right. So again, we're going to start with our pretty quadrantal angles. We start at 0, we go up to pi over 2, then down to pi, then to 3 pi over 2, and we finish off the rotation at 2 pi. Okay? We're dealing with our sine function, so that means we want the y values, right? The y values as we go around the function. So again, you can refer to this. Hopefully now you're starting to remember them. Sine starts at 0, goes up to 1, back down to 0, then down to negative 1, and then ends at 0. Okay? And then to fully complete our transformation here, now that we know what sine x is, we have to figure out what negative 1/2 sine x is. So this is the same as we're just saying we're going to multiply all of our sine values by negative 1/2. So negative 1/2 times 0 is 0. Negative 1/2 times 1 is negative 1/2. Negative 1/2 times 0 is 0. Negative 1/2 times negative 1/2 is positive 1/2. And negative 1/2 times 0 is 0. Okay. So now I have all of my points. I have my x's. And I have my outputs, my y's. So notice my y's are from 0, negative 1/2, and 1/2. So if we say this is 1, then 1/2 would be maybe there. Okay. All right, so I'm going to go ahead and put in my points. Okay, we know we're going to 2 pi. Half of that distance would be pi. Half of that distance would be pi over 2. And then our last one is 3 pi over 2. All right, so at 0, we're at 0. At pi over 2, we're at -1/2. I'm going to just put my dot right there in the middle of it. At pi, we're back up at 0. 3 pi over 2, we're at +1/2. And pi over 2, we're back down at 0. Okay, so we connect our dots. Again, we should have nice semicircle type shapes. And you can obviously see that our graph has been squished, right? We have squished it. You can think about this as a, as a vertical shrink, right? But notice we didn't just vertically shrink it, we also reflected it around the x-axis, right? Because normally a sine curve starts at 0 and goes up, and this one starts at 0 and goes down. So our curve is like reversed as to what it normally is. Okay? All right. So on both of these, we have looked at sine functions. Sine functions are pretty easy, right? And the changes that we've seen in them were vertical changes where we multiplied the y by something, right? This is just our y value, and this is saying we're going to do -1/2 times our y value. So I want to show you one where the change, where we have a multiplication, instead of it being outside the function, is inside the function, okay? So let's look at this last one for section 4.1a. So notice here, the difference is we're multiplying on the inside. And when we're multiplying on the inside, if you remember from college algebra, our x's were kind of on crack. They did the opposite of what we were thinking. So here, if we're multiplying the x's by 2, that's actually going to be a horizontal shrink. And when we used to edit our little XY tables, we would do the reciprocal value. So instead of multiplying by 2, we would divide by 2. Okay? So to kind of alleviate that craziness of backwards thinking, what we're going to do here, because we still want to end up with those nice quadrantal angles, right, as we go around, we want to make sure that whatever gets plugged into this ends up being a nice quadrantal angle. In other words, if we want x to end up being one of those nice quadrantal angles, okay, then we need to figure out what does 2x need to be, okay? So what does 2x need to be so that whenever I plug in my x, that ends up being one of those nice quadrantal angles. Otherwise, we're going to get really funky y values, okay? So what I'm going to do is I'm just going to figure out what that adjustment is. I'm going to take this 2x, whatever is inside my cosine, and I'm going to put it between the start and end values of the period that I know a pretty cosine curve uses. So we know that that period goes from 0 to 2 pi. So I'm going to say this 2x, or whatever's inside this cosine, has to be between 0 and 2 pi. Okay, because I want to make sure that when I plug my x values in, whatever they happen to be, that once they get plugged in and simplified in here, they end up being those nice quadrantal angles. Okay, so now I just got to solve this. To solve this, we just divide everything by 2, right, to get x by itself. So I get 0 is less than or equal to x is less than or equal to pi. Okay, so this is telling me the interval that I need to use. This is the interval I need to use to get those pretty quadrantal angle values. Okay, so I'm going to go ahead, and before I go any further, I'm going to go ahead and just put those down here. So instead of going from 0 to 2 pi, I want to go from 0 to pi, right? So let's think about that. If I'm going to come out here to pi, what's halfway between 0 and pi? Well, halfway between 0 and pi would be pi over 2, right? And then what's halfway between 0 and pi over 2? So between 0 and half a pi would be quarter pi, right? Or pi over 4. So that means for this particular function, we're going to be going by unit measures of pi over 4. So this is 1 pi over 4, 2 pi's over 4, and my third one would be 3 pi's over 4. So now I know my values. I start at 0, I go to pi over 4, I go to pi over 2, I go to 3 pi over 4, and then I end at pi. Okay. Now, let me show you why I did this, and then we'll go back and do the period and the amplitude and all that. So the reason that I adjusted, or I configured, if you will, specific x's that I chose is because now if I plug those in to cosine of 2x, right? And I actually don't really need this. I don't really need this column, right? If I were to plug 0 in here, I would get y is equal to cosine of 2 times 0, right? Or in other words, just cosine of 0. And we know that our cosine of 0 is our starting point, right, for going around and getting the cosine curve. So our starting point for cosine of 0 is 1, right? And then if I do the same thing here, cosine of 2 times my input, so 2 times pi over 4. Well, if I do 2 times pi over 4, that gives me cosine of pi over 2, right? Because my 2 and my 4 reduce. And notice cosine of pi over 2 is my next point, right? Here's pi over 2. If I want the cosine value of it, I look for that x value, which is 0. So basically what I did is I ensured that whatever x's I picked, when plugged into this function that has some kind of multiplication on the inside, what I would end up with is those nice quadrantal angles. Okay, so I can go through and simplify each of these. You don't necessarily have to, but I will just to go through it. So this one I'll get cosine of 2 times pi over 2, right? Here my 2's cancel, and this just gives me cosine of pi. Here we have y equals cosine of 2 times 3 pi over 4. My 2 and my 4 are going to reduce. So this just gives me cosine of 3 pi over 2. And then on my last one, y equals cosine of 2 times my input, which is now pi, which is just cosine of 2 pi. So if you look at it, I did it correctly because now all of these cosine values, these are just my quadrantal angles, right? So I basically chose x's so that when I plugged them into this function that has multiplication on the inside, once that multiplication took place, what I ended up with is exactly my quadrantal angles: 0, pi over 2, pi, 3 pi over 2, and 2 pi. So I can still go around and just use those nice x values of 1, 0, -1, 0, 1. Okay, so I'm going to go ahead and fill in those other ones. 1, 0, -1, 0, 1. Okay, so those are the values that I'm going to go ahead and graph on here. So I need a 1 and I need a -1. Excuse me. So at 0, I'm up at 1. Pi over 4, I'm down at 0. Pi over 2, I'm down at -1. 3 pi's over 4, I'm back up at 0. And at pi, I'm back up at 1. So you can see we still get that same cosine curve. The only difference is it's been squished in horizontally, right? To where now we get this full cycle by just going a distance of pi for our period versus 2 pi. Okay. Now I want to make sure that we did it right. I don't want to just get my answer off my graph. So I'm going to go back up here and check my period and check my amplitude just to make sure I did it correctly. Okay. So remember, our period we get from doing 2 pi over the absolute value of b. Okay. Remember, b is whatever is in here being multiplied to your x. So this gives me 2 pi divided by the absolute value of 2. So that's just 2 pi divided by 2, which gives me pi. So that tells me I should be able to complete my cosine curve with a period length or a distance of pi. And notice that's what we got down here, right? It took me exactly a pi distance to complete one cycle of my cosine curve. Okay. Then I want to look for amplitude. Amplitude, remember, we get from the a value that's in front of our cosine or sine curve. So we do the absolute value of b, which in this case, if there's no number written there, is an implied 1, right? And the absolute value of 1 is 1. Okay. And if we double check our chart here, we can see that our maximum value is 1, our minimum value is -1. So the distance between that vertical center and my maximum, or that vertical center and my minimum, is indeed 1. Okay. And then we want to see if there was a reflection. Remember, reflections come from having a negative either inside or outside the function, right? And here we had no negative, so we're going to say none. No negatives being multiplied inside or outside the function. Okay. And we can also tell by our graph, right? We know a cosine curve normally starts up at 1 and then kind of swoops down and then ends up at 1 again. So if there had been a reflection, this would have been flipped, right? It would have started at -1 and then kind of swooshed up to +1 and then ended back down at -1. Okay. All right, so the last thing I want to show you is an example. I'm just going to use the same problem, but I want to show you where it says, okay, what if we extended it over 2 periods? Okay, so we can either take the one that we have here and just extend it further to the right, or we could extend it to the left. So I want to show you both directions because I know there will be some like this on your worksheet, I believe. So I'm going to go ahead and just copy the function I have here. So this is pi over 4, pi over 2, 3 pi over 4, and pi. Okay, so notice we have a pi distance to complete one full cycle, right? With each little tick mark that we have written here, this is a distance of pi over 4, right? So this is 1 pi over 4, 2 pi's over 4, 3 pi's over 4, 4 pi's over 4, and that gives us our 1. Let me go ahead and 1, -1. Let me go ahead and draw in this one that we already have. All right, so we could keep extending out to the right by continuing to count by pi's over 4. So I'm going to go ahead and do that. I'm going to use a different color. So this is 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. So my next one would be 5 pi over 4, and then 6 pi over 4. Now 6 pi over 4 reduces, right? I can reduce that to 3 pi over 2. Okay. So 5 pi over 4, 6 pi over 4, 7 pi over 4, and then 8 pi over 4. And 8 pi over 4 reduces to 2 pi. Okay. So obviously if one rotation is pi, then 2 rotations would be 2 pi. So I'm just going to repeat these outputs. So we start up at 1, then we go down to 0, then we go down to -1, and then back up to 0, and then back up to +1. So we can just continue on this cosine curve. Okay, so notice here, from here to here, this is 2 periods, right? Okay. Or we could do our second period going to the left in the opposite direction. Okay, so I'm going to show you that also. Either one is acceptable to me. On MyMathLab, if it has you choose the correct graph, sometimes they extend the period to the right, sometimes they extend it in the negative direction. It just depends. So I want to make sure you've seen it both ways. So again, if I want to extend it, I'm still counting by pi's over 4. So if I go in the negative direction, this is going to be negative pi over 4, right? And then negative pi over 2, and then negative 3 pi over 4, and then negative pi. So that one was actually an easier one to write these down because we use these same measurements, right, just in the negative direction. Okay. And then I just continue the curve on. So if this is up at 1, this is going to come down to 0. This is going to be -1, back up to 0, back up to 1. So we go ahead and draw in our curve. Okay. So notice from here to here, probably wasn't the best way to write it. This is also 2 period lengths. Okay. So it doesn't matter to me. Like I said, if you want to take your original graph and extend the extra period to the right, or take your original graph and extend your period to the left. If it tells you specifically, make sure you do it in the way in which it tells you to. Okay? All right, so that is the end of section 4.1a. There is another video for 4.1b that you need to watch before completing the 4.1 assignment. So make sure you do that so you see all the instruction first.